Good afternoon, everyone. Welcome to today's webinar. I am Reese Robinson in the training department, and today's webinar will be boilers and systems, features and applications. Our presenter today is Søren Mortensen. He's the application manager in the industry segment out of our headquarters in Denmark. And he's by education, he's a marine engineer, and he's got a lot of experience with boilers, marine applications, and the biofuel industry as well. And so he'll be covering a lot of the basics with regards to boiler systems, features, and applications. A little housekeeping note today, everyone should have a chat box in the bottom right of your little control panel for the webinar today. So you are all muted. If you do have questions, please type them into the chat box, and I will do my best to answer those questions. If it's more or less a simple answer that I think I can answer on my own, I'll just type in the answer there. If it's something for Søren, then I'll wait for a good opportunity to stop him, and then I'll repeat the question to him and then have him answer those questions. We are recording this session, so after we're finished, we'll have a recording available to everyone. That will be posted to the U.S. training website for everybody to view, and then you can share that with your friends and colleagues and coworkers and anybody in the business that you think would benefit from this. And so with that, I will hand it over to Søren for our presentation today.
Thank you very much, Reese. And what we are going to talk about today is boilers and systems. In this presentation, we will cover the below topics: boiler types and design, the components in the boiler house, how to control the level in the boiler, the condensate systems, and last but not least, sizing of steam boiler feed pumps. Boiler types. Steam or hot water boilers is often just a matter of level. The design is mostly the same, but pressure ratings differ, and of course the equipment connected to the boiler, like safety valves and all that, is different, but the genuine boiler design is the same. How are thermal oil heaters or boilers built? Well, they are built mostly the same way as the steam and hot water boilers are. And what we have here is a horizontal fire tube boiler. And another type is a modern water tube boiler, which can be fitted with multiple overhead steam vessels. This one only has one. I'm pointing at it right here on the right on your screen. One overhead steam vessel, and that is normally the standard on smaller water tube boilers. Water tube as hot water heater boiler, yeah, can be used, but normally they are too expensive as to use as a hot water heater. If we continue to the boiler house components, if we start on the left of the screen, in many industrial applications we have a condenser to make sure that the condensate that we are taking home from the production facilities or process, that comes back as water and not as water and steam. Then we go to the condensate tank, where we add boiler feed make-up water, and we have our make-up water treatment plant. When we have the right condensate and it's been conditioned so it's ready to re-enter the boiler, we pump it up in the deaerator with the condensate pumps. And from the deaerator we take with the feed pumps and pump the water into the steam boiler. The steam boiler can be equipped with an economizer, but it's not all boilers that are depending on application. The deaerator, the reason for going through the deaerator is because it is the component that is giving us all the challenges in our boiler feed applications. It's, as the word indicates, used to reduce the oxygen and the carbonic acid in the boiler feed water. And that is simply to reduce the corrosion, reduce the risk of corrosion in the steam boiler. The deaerator consists of largely just a large vessel, and then we have a supply of condensate in the top, which we spray out over some trade sections, some baffle plates, and then we have a level of water in the deaerator. We heat that water with heating steam from our steam boiler, and on top we have an air vent to make sure that we have a slight overpressure in the deaerator. And then in the bottom we take out the deaerated water to the feed water pumps. We have two types of deaerators, and in this session we will concentrate on one of them. That's the one with the thermal principle, where we run at a typical pressure of 17 psig, and that gives us a liquid temperature of around 221 degrees Fahrenheit. Normally used in smaller plants. The vacuum principle deaerator on the right is running on a very low pressure, 2.9 psig, and have a vacuum pump installed, and that is used normally for steam turbine operation, and that principle will not be covered more in this presentation. If we go through the economizer, we have, of course, a wish to take out as much heat in the flue gas as possible. And if we have the flue gas inlet or the exhaust gas inlet from a main engine goes through the economizer, and then we have the cooled flue gas to stack or to funnel, depending on which installation. And if it's a land-based, then we have the cold water in the top. If it's marine-based, then we have a steam outlet. Why it's done like this, we can see later when we see how they are installed. And on the land-based, here we have a preheated water out, and on the marine-based, we have boiler water in. The economizer on land-based boilers, we have, of course, still our deaerator, we have our boiler feed pumps, but now we have made a twist on the piping so that we can run through the economizer and preheat the feed water more than we have done in the deaerator, and run into the boiler with very, very hot water, and of course giving the complete boiler system a higher efficiency. When we are talking marine-based boilers and economizers, they are built in a different way. Because we have so much heat from the exhaust gas from the main engine, we are actually capable of shutting down the steam boiler. We are actually capable of shutting down the steam boiler during transportation. That means when the vessel is sailing, we can shut down the steam boiler and then maintain the steam pressure in the boiler just with our economizer. But we need to circulate the water in the economizer, and that is done with a circulator pump sitting here in the bottom of the steam boiler, and that gives us some challenges. As I'm written up in the higher left corner, we have a high inlet pressure to the pump. Yes, we have, because the pump is exposed to the full boiler pressure. That means if we have a 220 and 50 psi boiler, then we have an inlet pressure of 250 psi to our pump, and that gives us some challenges, but we can deal with that with an air-cooled top pump, a CR pump with air-cooled top. And then of course we also have, corresponding to the higher pressure, we also have a high temperature on the water. How to control the level in the boiler? Now we come to the tricky part. On-off control, that is probably the most common used boiler feed system in the world, because every small boiler in all small applications, small steam systems, they mostly run on-off. It's only when we are talking larger boilers that we are speed controlling or controlling the level in the boiler with a valve. But what we are talking here in the US, a lot of steam boilers are run with a control valve, and we'll go through that later. The on-off control we simply have over here in our level control system, 2 switches telling the pump when to start and when to stop. Cheap system works fine, but it gives us some challenges with the cavitation in the pumps when they start, and we expose the boiler to mechanical stress due to the very large variation in water that is pumped into the boiler. When we start the pumps, they run full speed and simply take as much water from the deaerator and pump it into the boiler as fast as possible. And that means that the boiler receives a relative large amount of cold water, and that is giving mechanical stress in the boiler, and it will decrease the natural boiling of the water in the boiler, because that the water is cooled down. That was on-off control. Then we go further to the feed valve system. We still have our deaerator here on the left, our feed pumps, and our boiler, but now we have equipped the pipe to the boiler with a feed valve. And now this valve is controlling the level in the boiler. We have a level sensor on our boiler giving maybe a 4 to 20 milliamp signal to the motorized or to the pneumatic operated feed valve that will open and close corresponding to which level we have in the boiler. When having a feed valve installed, we have the risk of the feed valve closing completely. If the boiler is not calling for water, the feed valve will close, and if we continue on running our pumps with the feed valve closed, then we will burn off the shaft seal. That means when we have a boiler feed with feed valve, we need to install a bypass to ensure that we are pumping enough water through the bypass and through the pumps to cool down the shaft seals sitting on top of the CR pump. That of course means that we are pumping excessive amounts of water, and that gives us a higher energy consumption. Now that's not normally what we are concerned about in boiler feed solutions, but we are pumping excessive amounts of water and using more energy than needed. In the better built system or the better design system, they are put in a control valve in the bypass system, making sure that we are not pumping water through the bypass system when the feed valve is open, maybe 10% or something like that. That was boiler feed with feed valve. If we build the system a little bit smarter, then we put on a frequency converter on our CR pumps and having a pressure sensor controlling the speed of the pumps so that we maintain a constant pressure in front of our feed valve. When we have a boiler feed system with the feed valve, when the feed valve is closing, we will crawl up the pump curve and end up running at maximum pressure of the pump at low flow. With this smarter installation or application we have, where we have the pressure sensor installed, the feed pumps will slow down in speed and hold or maintain the correct pressure due to the pressure sensor, so that we will maintain a constant pressure in front of our feed valve. We still have the bypass, ensuring that we are pumping enough water to cool down our shaft seals. But the pressure in the bypass system is now lower because we are maintaining the constant pressure in front of our feed valve.
Soren, we have a question from, forgive me for pronunciation, but it's from a Mr. Magnuski. And the question is, at what temperature do we take the NPSHR graph, and how do we correct graph for high temperature? So, and I think we will answer that question later when you're showing a performance curve, but his question is what temperature is the NPSH graph based on, and then how do we correct for NPSH for 221 degrees Fahrenheit?
Yes, I will come back to that, but I would like to answer it
okay.
Right away. Then we can take it later as well.
Okay.
Actually, the NPSH curves are drawn on 20 degree C de-aerated water. That means that the NPSH curves you find on web caps, on product center, and in the data sheets, they are not correct when we are talking boiler feed and we are operating with 221 degrees C or degree Fahrenheit water. That's also why when we are talking boiler feed and we are sizing the pumps, we put in a safety factor. And that safety factor will come back to how high should that be, or how many feet of water do we put on as a safety factor. I hope that was answered enough for the moment, and we will, as I said, come back to it later.
Okay, and there was one additional question which I also think will be answered later. Is it okay to control the feed water pumps via, well, maybe not. Is it okay to control the feed water pumps via steam header pressure?
I don't understand what...
Yeah, I think maybe we'll get back to that when we talk about speed control when you have multiple boilers. But the question, again, I'll repeat it as stated, is it okay to control the feed water pumps via steam header pressure? So I think what he's saying is that if we're monitoring the steam header pressure, and I believe when he says steam header, the steam going out to the process, is use this as a feedback to control the pumps.
Yes. Now I got it. Yep. No, we can't use the steam pressure. When we look at a steam boiler, we should actually look at the steam boiler as a vessel containing water. And the pressure is just something that we have to overcome. The pressure is controlled by the burner in the boiler. And we don't want to have anything to do with the pressure in the boiler. That is the burner and the boiler safety system controlling that. That is not a pump's or pump manufacturer's obligation to do anything about the actual boiler pressure. That's the burner manufacturer who's controlling that. We just have to overcome the pressure in the boiler. So we can't use the pressure in the boiler as an indicator or as a control to our speed control pumps. I hope that was sufficient.
Okay, thanks, Soren.
I will continue to the Grundfos way of, the intelligent Grundfos way of doing boiler feed. If I take my pumps from before with the integrated frequency converter, or we can take a CR pump with a CUE hanging on the wall, then I can remove my feed valve that was positioned down here, take that one off. I don't need it, because I can take my signal directly from the level sensor, put that signal into my frequency converter, and then I can run the boiler system exactly as I do run an open tank system. I just control it on level. If the boiler is calling for water, then the pumps will speed up. If the boiler is saying, okay, I have enough water, I don't need any more, then the pumps will go down in speed. And if they are full, or if you reach the maximum level in the boiler, the pumps will simply stop. And again, when the level sensor senses that now the boiler calls for water, then the pumps will start up exactly like we do if we have a low flow stop function in other boiler, or not in boiler, in other applications where we use the frequency converter. So this system has many good things. It's if we take a look at a feed valve, for example. When we have a feed valve, we need to have a certain pressure loss over the feed valve. Otherwise, the feed valve doesn't work. That means when we have a pressure drop over a feed valve, we need larger pumps. We need more power to pump the water through the feed valve and into the boiler. We get rid of this now. That means we can design smaller pumps. We can, again, we avoid the bypass. That means when I am installing my complete system, I don't have to use the money for a bypass, because I don't need it now, because my pumps will simply stop. So there are some very, very good things about this system, and I think the best one is that you actually avoid your feed valve. I don't know the price of a feed valve in the US, but I know the maintenance cost of a feed valve is very, very high, and you avoid that. On a CR pump with a frequency converter, there is almost no extra maintenance costs. So it is a win-win situation to get rid of the feed valve and put on the frequency converter on the pump and let them run the level in the boiler.
Okay, Soren, this is a very interesting slide. We've got a couple questions about this one. Number one question is, how do we control the heat around the seals on this type? So when we have speed control pumps, I'm thinking the question is, how do we avoid seals heating up due to lack of lubrication or something when we using frequency control and there's no bypass?
Yes, when we set up the frequency converter for running this type of installation, then we set the frequency converter to a minimum speed, ensuring that when the pump is running, we are always pumping water into the boiler. And pumping water into the boiler means that we are cooling down the shaft seal. Then, when we reach the maximum level in the boiler, the pumps will stop. And if we have a very low steam consumption, then the pumps will actually run as an on-off control. And that works perfectly because the frequency converter can start and stop the pumps, yeah, many times per hour without overheating or anything. So we can run at low flow a start-stop function, and when the boiler calls for more water, it will go into continuous operation and ensure cooling of the shaft seal.
Okay, so basically, if you're using speed control in this type of arrangement, then you must have controls that are set up such that the pumps are actually switched off when the boiler water level gets sufficient. And so basically it takes some strategy in the controls to make this successful. In other words, you can't just buy a couple drives, mount them on a wall, hook them up for level control, and think that it will be successful. You actually have the strategy set up in the controls to accomplish the protection of the pumps so that they don't run, so that they're not running against a closed valve, and there's always water moving through the pumps.
Yes, exactly. Exactly.
Okay.
That's also why I recommend to use the COE. Yeah, of course I do that because it's a Grundfos product. But in that we have the right solutions for doing this system.
Okay, great. And then an additional question around the same topic is, so basically there's no bypass required, and I think we kind of answered that question,
Yeah.
that because we have the controls deployed in the pumps to switch them off when there's no demand, the bypass is not required.
Yeah, exactly.
Okay, great.
I will continue. We have covered the way of feeding the boiler. I will go to some of the, when we are talking boiler feed for multiple boilers. If we run the direct boiler feed the Grundfos way, then if we have two boilers, then we need two sets of pumps. That means we will have an installation looking like this. And we still have the deaerator, and we have two sets of E-pumps here, and two sets of E-pumps here for boiler B. And we still have, of course, the steam boiler with its economizer and steam outlet, and then the steam outlets can be connected to each other to a common line on the end, but that is not in our scope to talk about that today. That is when we do the direct boiler feed. If we have multiple boilers and we don't want to run this direct system, then we have to have a control valve on each boiler, and then we can use a control MPC to control a number of feed pumps. Then I have drawn 4 pumps on this one that could go from 2 to as much as 6. We have a pressure sensor installed on the common feed line for the boiler feed, and then these 4 pumps are running a constant pressure, ensuring a constant pressure in front of the feed valve, no matter the water intake to the boiler. On this system, because we don't know how the pumps are running and we don't know which boiler is calling for water, seen from the pump's point of view, we simply need a bypass. We can't do without the bypass because we don't know when the boilers are calling for water and when they are not. And now, can you find the design error? I've written it down here. I'm not, you're not going to ask, and we're not going to spend 5 minutes on who should be the one to have answered the right way to the question. But if you take a look at how the economizers are installed, I have my control valve in between the inlet and outlet to the economizer, right here. And that doesn't make any sense, because if my control valve is fully open, I will have no water through my economizer. And if my valve is closed, I will have all the water through the economizer. and my control valve wouldn't work. So that was just a little design error that always can raise some interesting questions.
Okay, Soren,
Yes.
we have a
yes.
yeah, sorry. We have a question. This is going probably back a couple slides. I'll ask the question. You'll probably figure out which slide it was. The what type of signal is required from the boiler level control as an input to the frequency drive?
Yeah, we go back to this one. Yes, the frequency converter can react both to 0 to 10 volts, 0 to 20 milliamps, and 4 to 20 milliamps. But since we are talking industrial installations, I will always recommend 4 to 20 milliamps because it is the most durable signal type that we know of. Running on volts and from 0 to 20 milliamp is yeah, could call it unstable, but it's not. It can be influenced on disturbances on the grid and harmonic distortions and other stuff. So they are not as stable or as good to use as the 4 to 20 milliamp signal.
Okay, and then kind of a follow-up question to that one, Soren. Can you split one 4 to 20 signal to both frequency converters or both drives?
Yes, I can do that. I need then a control box and a signal splitter. Signal splitters are produced by any major component producer, so you can get them from Schneider Electronic, from Rockwell, from you name them, Siemens. They all do them, so it's an easy component to find and install.
Okay, and then another question that might have to do with the next slide, something about comments about non-return valves. Shall they be installed? And I think I think they're shown there, just maybe a little bit differently. But the question was, shall parallel pumps be separated by check valves or non-return valves? I think they just want to confirm that.
Yes, they must always be. And the control valve must always be on the pressure side of the pump. Otherwise, if we have the control valves or non-return valves on the suction side of the pump, we will end up having a pressure loss or pressure drop over the non-return valve on the suction side, and we don't want that. And we will have the full boiler pressure on a non-running pump, and that can create some problems for the shaft seal.
Okay, great.
Any further questions, Reese?
I think we're good for now.
Good, we'll continue. And we will jump directly to the pumping of condensate. When pumping condensate, it's just a matter of moving water from one open tank to another open tank. It would be from, like shown on this drawing, from a condensate tank directly to the deaerator. And normally in many applications, we see that on-off pumps are used, and that works perfectly fine. But if we want to have the full efficiency of our deaerator, then we can have maybe up to 10% higher efficiency in the deaerator with running the condensate pumps as speed control pumps, because we will have a continuous and constant degassing of the water. When we are using on-off pumps, we will pump not cold water, but relatively cold water into the deaerator, and that will stop the process of degassing the water. One thing to think about on condensate systems is that the water is hot 200, maybe 210 degrees Fahrenheit, and that is challenging when we are talking suction on the pump. So we need to take care of or be aware of the NPSH, and NPSH will get back to that later. If we take a look at return condensate even further, when we are out in large production facilities, we can have several condensate tanks in the production. And pumping from one condensate tank to another is normally done by on-off control. And there's normally not a reason for installing any frequency converters on that. Just again be aware that the pumps can be running in very hot conditions, water temperatures beyond 200 degrees Fahrenheit. And we can even have high pressure condensate systems where we are running above 250 degrees Fahrenheit and are using CR air-cooled tubs as condensate pumps. Yes, that was the condensate. Now we come to pump sizing. That is always the funny part of the boiler feed systems, because this is where we normally end up running into problems and pumps not sized correctly and all that. And why that happens, we will go through now. I have an US boiler system as my basis for my calculations, and I have a Cleaver Brooks boiler with 600 horsepower and 150 psi, and that is what is giving me the basis for all my pump calculations. And in the lower left corner down here I have written, never use the steam temperature. The pump will always meet the temperature from the deaerator. When we look at a feed pump, it will never know what happens beyond this line. It doesn't know if we are cooling the water down, if we are heating it up, whatever we do to it. So the feed pumps will never see what is happening on the right side of the drawing. The only thing that the feed pumps know is that it is given 222 degrees Fahrenheit water on the suction side, and we need to raise the pressure to a certain ratio. That's what we know. So never use the steam temperature or steam data for anything. It is always the water temperature from the deaerator that we use and the nameplate on the boiler, not the steam data. The rules, ASME code, requires the boiler feed pump be able to put water in the boiler at the evaporation rate at a pressure which is 3% greater than the highest setting of the safety valve. And that's simply a US design code, which, yeah, we just meet it and then say that's how we do it. And normally we add 25% to the flow as catch-up. That sentence I have stolen directly from Industrial Steam Incorporated, and large US-based company doing a very, very large amount of steam installations each year. We have some rule of thumb on when we are calculating on boiler feed, and that is also from ASME codes that I have. If I calculate the flow to my boiler, then I have a standard factor called 0.069 and multiply that with the horsepower of the boiler, then I'll get the flow. 41.4 gallons per minute, and then I have the head of the boiler. I need to recalculate because I have my 150 psi for the boiler, but I can't go into a pump sizing tool with 150 psi. I need to recalculate that to feet of water. And that gives me, again, a constant that I need to use, and then I have a correction factor for how much lighter the water gets when I start to heat it. If I have used cold water, I would have had 1 on the lower part of my equation here, but now, because I am dealing with 222 degrees Fahrenheit water, I have a correction factor of 0.955. That gives me a head of a boiler of 363 feet. During operation on this boiler, I'm only running the boiler at 75 psi. That means during operation, my pump only has to supply 182 feet of water. I have my my flow for the boiler that was calculated before to 41.4 gallons per minute, but due to the safety factor of 1.25 as catch-up, I end up with 54 gallons per minute as my design flow on my pump. And the head of the pump for design and safety factors will be 1.03 times my safety valve setting and the constant and the correction factor. That gives me a head of 374 feet. And then the question in the bottom, do we always know the safety valve settings? No, we actually don't. But you must never size a feed pump before you know what pressure settings we are running at. It is not our job as pump producers or as pump distributors, sales guys to inform about what is the pressure setting of a boiler. That should always come from the customer. Yes, now we have the design parameters for our pump. Now let's see what happens. Now we are talking another parameter, that is NPSH, net positive suction head. That means how much pressure do I need in front of my pump in order to not cavitate. That means how much pressure should I have so that the pump can run without cavitating and by that destroying itself. And we are talking two different NPSH values. We have the required and we have the available. The required is what the pump needs and is what is measured from the impeller, the eye of the impeller, and to the inlet flange. And the NPSH available is what pressure is available for us on the suction side of the pump in the piping system. To each pump is a corresponding NPSH curve. We have a normal pump curve here. On a fixed speed pump, we can't move away from that pump curve. We are always operating somewhere on this pump curve. That gives us an efficiency point, that gives us a power consumption point, and the curve in the bottom here shows us that we have an NPSH of 7.32 feet. Those 7.32 feet is what the pump needs of head in cold water. So now we come back to the question that was raised before: how do we correct to the fact that we are pumping 210, 20, 30 degree Fahrenheit water and the water is actually boiling on the suction side of the pump? If we take a further look on NPSH and what is happening when we are talking cavitation, what is happening is that at the eye of my impeller right here, because I'm sucking in the water, I am creating a lower pressure than the pressure in my suction line. That can create because I'm lowering the pressure, that can create steam bubbles to evaporate, or not to evaporate, to be created. And those steam bubbles are following the water flow. And when the steam bubbles are moving on the side of the pump waves, then as I go further and further out on my impeller, following my arrow, the higher the pressure gets. And suddenly, when the pressure is high enough, the steam bubbles in the water will implode. And when a steam bubble implodes in water, it will create a massive, massive pressure spike. And that pressure spike will eat up all material on the impeller vanes. And no material is yet to be found that can withstand the imploding of a steam bubble. Sorry. If we look at how it works, we have a pressure scale here, and our impeller inlet, and our impeller outlet. What happens is that I have my pressure here, and when I start to go into my impeller, I suddenly cross this fine line of vapor pressure. When I cross that one, my water turns to steam until I go up on the pressure side over here and build up pressure. That means in this area I have steam, and on this area I have water. Okay, we could then say I'll take a very sturdy impeller. It can withstand some cavitation, and I have a material enough so it will probably run for a couple of years before it breaks down, and then I'll just replace it. Yeah, you can have that way of thinking, but in boiler feed I don't like it, because when we have cavitation we don't know where we are on the pump curve. When a pump cavitates, I do not lie on my pump curve. I will maybe have a pump curve here, but actually the reason for drawing it is dotted is that we don't know where we are. We can be anywhere in this area on our pump curve. And if I am supposed to lie up here in order to pump water into my steam boiler, I don't want to run a pump down here, because then I have the risk of running low on water in my steam boiler, and I will end up with a boiler shutdown. That is not accepted. So we need to make sure that the pump is not cavitating. And let's see if we can calculate a little bit on that. To avoid cavitation, our system pressure needs to be higher than what is required by the pump. And when we are talking the NPSH of the system, we have the pressure available on the inlet of the pipe. That is our main pressure we need to be sure of that we have. And then we have HP, that is the pressure inside the deaerator. We have the HF, that is friction loss in the suction pipe. Then we have HV, and that is vapor pressure of the liquid. Vapor pressure, that's a little bit funny size, because it's actually a pressure that is working against our inlet pressure. And that is a pressure that is occurring due to the movement of the molecules in the water. And we'll see a little later how we calculate on that. Then we have the HGO, and that is the water level above or under the pump inlet. In boiler feed system we will always have a level above the pump inlet, so that we have to add the geographical height. And then we have the safety factor. As I mentioned before, when we were talking NPSH curve drawn with cold water, then we need to have a safety factor to make sure that we are not cavitating on hot water. We take the values from before, and place the deaerator 18 feet above the pump. And then my equation will look like here it does in the bottom. And as you will see, the two values from the pressure inside the deaerator and the vapor pressure of the liquid, they are always the same size when we are talking boiling water. And in the deaerator, we are boiling the water. We are heating up the water as much as we can under the given pressure. That means that the water is boiling exactly as you do when you are boiling potatoes at home. That means that the values that we have, the first two take out each other. Then we have 18 feet in geographical height. Then we take out 6 feet as a safety factor. And we have our 6 feet as friction loss. That means that we end up with a system head in front of our pump at 6 feet. And let us see if that is sufficient to size a proper feed pump. Now this is a pump that will suit the boiler we talked about before. And if I take a look at the NPSS value of a CR20 pumping 110 gallons per minute, then I'll end up with an NPSS H curve showing 8.6 feet. That is required by the pump. I need 8.6 feet in order not to cavitate in cold water. That's not good enough because we have only 6 feet available. Then I can take and equip my CR20 with a low NPSH stage. The first stage in the CR20 is a low NPSH stage. That is an impeller from the CR32, and that gives us a completely different NPSH value. Now I'm below the 6 feet. That means I require 5.8 feet at my pump. So that should be enough. I am good to go. Now this is very, very, very tight calculation because I have my 6 feet I require, or that I have from my system. I have my 5.8 feet required by the pump, and I have added a safety factor. Then is the good question, did I add enough in my calculation on my safety factor? In this equation I will say that I have added enough because the flow I go in to design with here is including the 1.25 times as catch-up. That means during normal operation I will never end out in this duty point on my curve. So if you take and add the 1.25 as safety factor and then give in 6 feet as a safety factor calculating the NPSH value, then we are good to go on the CR box. And if you are in doubt of anything calculating, put on 2 or 3 extra feet on your safety factor. Otherwise you'll end up having pumps breaking down all the time, and that is unfortunately seen way too often in boiler applications. Yes. Which pump to choose? I have sized my pump, figured out which one to use, and yeah, I go into Grundfos Product Center or web caps or wind caps on whatever platform you have to select your pumps, and yes, I can see this one is working in my boiler application. I'm fairly low in flow. I'm far down in my left side of the NPSH curve, so that should work. Actually, the NPSH curve on this one says 3.6 feet. That means this is a good pump to choose. That is how it's done when you go directly in webcaps and choose the pump. If you have time, you can find a little bit smaller pump, maybe with one stage lower, and then you can run at a little bit higher efficiency point, and you run the pump more detailed to the specific duty point. But it takes a long time, so if you just want to do the simple and safe solution, just go directly into to caps and choose your pump. And then I am working with this every day and have the time to fool around and find all the mistakes in caps. So this is also a part of my job, to play around with how can I size the most precise pump for the job. But you will never have the time to do that, because you should better sell pumps instead of detailed design and size pumps.
Soren, yeah, we have a question,
yes.
Soren.
Yes.
And it might be on a previous slide. The question is, what is H sub S? So it might be part of the calculation. Is there an H sub S there?
Yes, HS.
Okay, so that's our safety margin you were talking about.
Yes, yes, yes it is. And that is the one, if we are in doubt, put on 2 extra feet so that we add 6 feet in safety factor.
Yeah, I think if you're, for the audience, if you're looking at a CR pump data booklet, I think in the CR pump data booklet there's a worksheet where you can actually calculate NPSH, and I think in our example, our recommendation is to use 2 feet as the safety factor if you're utilizing a Grundfos CR data booklet or CR product guide.
Yes, yes.
And then there was one additional question. Do we calculate pump for operation parameters or max demand? I think that's referring to the pump sizing. Shall we select the pump for the normal operating parameters, or do we select the pump for max demand?
Yes, ASME code says that we should size the pump for the boiler data nameplate. That means it has nothing to do with operation. It's the boiler data that we are sizing for.
Okay, great.
So if we are running a boiler, a 150 psi boiler at 75 psi, we still need to size the pump for the 150 psi.
And also at the flow rate of the boiler nameplate horsepower.
Yes.
Okay.
Exactly.
So further justification for speed control, because then you can right size your pumps.
Exactly. Exactly. Yes.
Okay, that's all questions so far.
Which pump to choose? Yes. And just to, I mentioned before the economizers, and we can also advise our boiler customers to install economizers if they are not installed when we first talk to the customer, because retrofitting of economizers is very, very healthy business. Of course, it's good business for us because, as you can see on the drawing, if we have an economizer or several economizers, we need pumps to circulate the water in the economizers. The first economizer installed is the water is circulated by the feed pumps to the boiler. That was exactly the same as we saw before. Heating the water up before it enters the boiler. As you see, I have 223 degrees Fahrenheit water in my deaerator, and that water I am heating to 284 degrees Fahrenheit before it enters my boiler. Then I have some condensate heating, because I get a lot of I don't get much condensate return, so I have to have a lot of makeup water added all the time, and that is normally cold water, and I need to heat that before I will let it enter the deaerator. So I need a pump to circulate that, raising it from 127 degrees Fahrenheit to 171. And then I have my hot water buffer. This application was using a lot of water daily, and I could raise from Danish groundwater temperature of 50 degrees Fahrenheit to 131 degrees Fahrenheit, 13,200 gallons per day. That gave the customer a saving of 5,700 MCF natural gas per year, and a payback time less than 1 year. So that is again a good indicator or a good motivation for installing economizers on steam boilers. Yes, that was about what I was going through today. I will say thank you for your time and attention. Now you have gained valuable insight in the below topics: boiler types and design, the components in the boiler house, how to control the level in the boiler, the condensate systems, and sizing of steam boiler feed pumps. If you have any further questions, we will take them now, and Reese will be, as before, controlling the questions. Thank you.
Thank you, Soren. So I'd like to thank everybody for your participation today in this webinar. Again, it has been recorded, so you will each receive a link to our training website, and when it's made available, we will let you know. So everybody in attendance, I believe you signed in with your email address, so we have a list. So we will email you everybody the link to the recording itself, and other webinars we have on our training website. If you go to in your browser, type grundfos.us/training, you'll be able to go in there and find a list of there's a course listing there. There's a calendar that lists our courses, as well as live face-to-face training, as well as webinars. So please feel free to do that. And I will see if there's any additional questions here. It looks like question about